Schrödinger's cat revealed a paradox that quantum mechanics describes reality with extraordinary precision. But consciousness creating reality is a myth that physics abandoned decades ago. The quantum measurement problem, the question of how a probabilistic wave function yields a single definite outcome when measured, is one of the deepest puzzles in physics. But the answer is not consciousness. The answer, as demonstrated by Wojciech Zurek's decoherence theory and quantum Darwinism, is the environment. Every quantum system interacts with its surroundings: stray photons, gas molecules, cosmic dust, thermal radiation. And these interactions entangle the system with the environment, suppressing quantum interference and selecting stable pointer states that behave classically. The Schrödinger equation, the master equation of quantum mechanics, evolves the wave function unitarily without collapse. The Born rule converts the wave function's amplitude into probabilities. And decoherence explains why we never observe macroscopic superpositions, why Schrödinger's cat is always either alive or dead, never both. No conscious observer is required. The environment does the work. And the fine-tuning of the physical constants that make this ordered, law-governed, decoherence-enabling universe possible, the fine structure constant at approximately 1/137, the cosmological constant tuned to 1 part in 10 to the 120, the carbon resonance level predicted by Fred Hoyle to within a few electron volts, raises a question that physics cannot answer, but the evidence demands. Why are the laws this way? The consciousness mystics have no answer. The multiverse has no evidence. The evidence points elsewhere. What follows is a forensic examination of the claims, the physics, and the evidence. By the end of this video, you will understand what the quantum measurement problem actually is, in the language of the Schrödinger equation, the density matrix, and the Born rule, and why it does not require consciousness to resolve. You will understand decoherence, the physical process by which environmental interactions destroy quantum superpositions and produce the classical world we observe. You will understand quantum Darwinism, Zurek's framework explaining how the environment broadcasts redundant copies of pointer state information, making classical reality objective. You will understand why the von Neumann-Wigner interpretation, the claim that consciousness causes wave function collapse, was proposed, examined, and abandoned by its own originator. You will understand why biocentrism, Robert Lanza's claim that consciousness creates reality, fails as physics and as philosophy. You will understand the interpretations of quantum mechanics, Copenhagen, many worlds, Bohmian mechanics, objective collapse, cubism, and relational quantum mechanics, and what each does and does not explain. And you will understand the fine-tuning evidence, the extraordinary precision of physical constants acknowledged by atheist physicists from Fred Hoyle to Martin Rees to Leonard Susskind, and why this precision points not to consciousness, not to a multiverse, but to an intelligent, powerful, eternal creator. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us examine the evidence. The foundation is the Schrödinger equation, the master equation of quantum mechanics, the mathematical law that governs the behavior of every quantum system in the universe, from individual electrons to complex molecules to the quantum fields that permeate all of space. In 1926, Erwin Schrödinger, born 1887, died 1961, Austrian physicist, Nobel Prize 1933, formulated the wave equation. I h bar times the partial derivative of psi with respect to t equals h hat times psi. Let us define every term precisely. I is the imaginary unit, the square root of -1. Its presence in the equation is not a mathematical convenience, it is necessary. The imaginary unit ensures that the wave function evolves as a complex valued function with both amplitude and phase. And the phase is what produces interference, the defining quantum phenomenon. H bar is the reduced Planck constant. Planck's constant h divided by 2 pi. Its value is approximately 1.055 times 10 to the negative 34 joule seconds, or approximately 6.582 times 10 to the negative 16 electron volt seconds. H bar is the fundamental quantum of action, the smallest packet of action, energy times time, that characterizes quantum physics. Its value sets the scale at which quantum effects become important. Large compared to h bar, systems behave classically. Comparable to h bar, systems behave quantum mechanically. The fact that h bar has a specific, non-zero, finite value, and not some other value, is itself a feature of the fine-tuning of the universe. If h bar were significantly larger, quantum effects would dominate at macroscopic scales, and classical physics and the stable structures it enables would not exist. If h bar were 0, quantum mechanics would reduce to classical mechanics, and the phenomena that depend on quantum effects, chemical bonding, semiconductors, nuclear fusion in stars, would not operate. Psi, the wave function, is the mathematical object that encodes all the information about the quantum system's state. It is a complex valued function. At each point in space and time, psi has a real part and an imaginary part, or equivalently, an amplitude and a phase. The squared magnitude of psi, the absolute value of psi squared, gives the probability density for finding the particle at that point. This is the Born rule, and we will return to it. The wave function is not directly observable. You cannot see psi, measure psi, or photograph psi. What you can measure are the consequences of psi, the probabilities of different outcomes, the interference patterns, the correlations between entangled particles. The wave function is the most complete description of a quantum system that quantum mechanics provides. It contains everything the theory can say about the system. H hat, the Hamiltonian operator, represents the total energy of the system. It encodes the kinetic energy, energy of motion, and the potential energy, energy from forces and interactions of the system. For a particle in a potential v of x, the Hamiltonian is h hat equals negative h bar squared over 2m times the second derivative with respect to x plus v of x. The first term is the kinetic energy operator. The second is the potential energy. The Hamiltonian determines how the wave function evolves in time. It is the engine of quantum dynamics. A different Hamiltonian means different physics, different forces, different interactions, different behavior. The specific form of the Hamiltonian for each system encodes the physical laws that govern it. The Schrödinger equation is deterministic. Given the wave function at one time, it uniquely determines the wave function at all future times. There is no randomness in the equation itself. The development is smooth, continuous, and completely predictable. The equation is also linear. If psi sub 1 and psi sub 2 are both solutions, then any linear combination, A times psi sub 1 plus B times psi sub 2, where A and B are complex numbers, is also a solution. This linearity is the mathematical origin of superposition, the defining feature of quantum mechanics that makes it so profoundly different from classical physics. If a particle can be in state A, passing through slit 1, and can be in state B, passing through slit 2, then it can also be in the combination A times A plus B times B, passing through both slits simultaneously, with amplitudes A and B determining the relative weight of each path. The combination is not a metaphor. It is the mathematical description of the quantum state. The particle is in both states at once, not in one or the other with some probability, but genuinely in both, with the two components interfering with each other. This is counterintuitive. It contradicts every classical intuition about objects being somewhere with a definite state. A classical ball thrown at a wall with two holes goes through one hole or the other. A quantum particle goes through both. The two components of the wave function, one passing through each slit, meet on the other side and interfere. Constructively, at some points, bright bands on the detection screen, and destructively at others, dark bands. This interference pattern is the experimental signature of superposition, and it has been confirmed with photons, electrons, neutrons, atoms and molecules as large as C60 fullerenes, Zeilinger, 1999, and even larger organic molecules. The Born rule, proposed by Max Born in 1926, German physicist, born 1882, died 1970, Nobel Prize 1954, connects the wave function to experimental outcomes. The probability of finding the system in state phi sub I upon measurement is P sub I equals the magnitude of the inner product of phi sub I and psi squared. The inner product is a mathematical operation that measures the overlap between two quantum states. The Born rule says, square the overlap and you get the probability. This rule is not derived from the Schrödinger equation. It is an additional postulate, an empirical rule, confirmed by every quantum experiment, but not logically necessitated by the wave equation itself. The Born rule is where probability enters quantum mechanics. The Schrödinger equation is deterministic. The Born rule is probabilistic. The tension between these two, deterministic development followed by probabilistic measurement, is the heart of the measurement problem. The uncertainty principle, formulated by Werner Heisenberg in 1927, German physicist, born 1901, died 1976, Nobel Prize 1932, establishes a fundamental limit on the precision of simultaneous measurements. Delta x times delta p is greater than or equal to h bar over 2. Delta x is the uncertainty in position. Delta p is the uncertainty in momentum. The product of the two cannot be reduced below h bar over 2, no matter how clever the measurement apparatus, no matter how advanced the technology. This is not a limitation of instruments. It is a limitation of reality. A quantum particle does not simultaneously have a precise position and a precise momentum. The uncertainty is intrinsic. The measurement problem arises because the Schrödinger equation and the Born rule appear to contradict each other at the moment of measurement. The Schrödinger equation says the wave function evolves smoothly, deterministically, and linearly, preserving all superpositions, never selecting one outcome over another. The Born rule says that upon measurement we find one definite outcome with a probability given by the squared amplitude. But if the Schrödinger equation governs all physical systems, including measurement apparatus, then the apparatus itself should enter a superposition entangled with the quantum system. John von Neumann formalized this in his 1932 book, Mathematical Foundations of Quantum Mechanics. Von Neumann, born 1903, died 1957, Hungarian-American mathematician and physicist, showed that the combined system plus apparatus state after a measurement interaction is sum over I of C sub I times the state S sub I of the system tensor product with the state A sub I of the apparatus. This is a superposition of all possible outcomes, each correlated with a different apparatus pointer reading. The apparatus is in a combination of pointer reads up and pointer reads down, entangled with the system being in spin up and spin down. Yet we always observe one definite result. The apparatus always shows one reading. The pointer is never in two positions at once. The gap between the superposition predicted by the equation and the single outcome observed in the laboratory is the measurement problem. And it is one of the deepest open questions in the foundations of physics. Schrödinger himself dramatized the problem with his famous thought experiment in 1935. A cat inside a sealed box with a radioactive atom, a Geiger counter, and a flask of poison. If the atom decays, the counter triggers, the flask breaks, and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics describes the atom as in a superposition of decayed and not decayed. The Schrödinger equation, applied to the entire system, atom, counter, flask, cat, predicts that the cat is in a superposition of alive and dead. This is absurd on its face. No one has ever observed a cat in a superposition of alive and dead. Schrödinger's point was not that cats actually exist in superpositions. His point was that the formalism, taken at face value, predicted something manifestly contradicted by experience. The resolution of this paradox is the measurement problem. Decoherence resolves the paradox, or at least dissolves the appearance of paradox. The cat is not in a sealed, isolated box in any realistic sense. The cat is made of approximately 10 to the 28 atoms. It interacts with air molecules, thermal radiation, photons from the laboratory lights, vibrations from the floor. These environmental interactions entangle the cat with its surroundings, decohering the superposition in a time so short it cannot be meaningfully measured. The alive and dead components of the cat's wave function become effectively separate. They no longer interfere with each other, long before any human opens the box. The cat is always alive or dead, never both, because decoherence has already enforced classical definiteness. No consciousness required. This is where the consciousness interpretation enters and where the prosecution begins. The idea that consciousness causes wave function collapse has a specific history. A history that begins with a mathematical observation, passes through a philosophical speculation, and ends with its own originator abandoning it. Understanding this history is necessary because the claim "consciousness creates reality" is not a discovery of modern physics. It is a discarded interpretation from the 1960s that persists only in popular culture. John von Neumann, born 1903, died 1957, Hungarian-American mathematician and physicist, established the formal mathematical treatment of quantum measurement in his 1932 book, Mathematical Foundations of Quantum Mechanics. Von Neumann analyzed the measurement process using the tools of linear algebra and showed something that would puzzle physicists for decades. The collapse of the wave function could be mathematically placed at any point in the measurement chain. The quantum system interacts with the measurement apparatus. The apparatus interacts with the environment. The environment interacts with the observer's sensory organs. The sensory organs interact with the brain. At each stage, the Schrödinger equation predicts that the next link in the chain enters a superposition entangled with the previous one. Von Neumann showed that the final result, a single definite outcome, is independent of where in this chain one postulates the collapse to occur. The collapse could happen at the detector. It could happen at the amplifier. It could happen at the recording device. It could happen at the observer's retina. The mathematics does not select a specific point. This is sometimes called von Neumann's chain, or the von Neumann cut. Von Neumann himself did not claim that consciousness causes collapse. He identified the mathematical ambiguity, the freedom to place the cut anywhere in the chain, but did not resolve it. He noted that the chain must terminate somewhere, and he observed that one possible termination point is the observer's abstract ego, the subjective experience. But this was a mathematical observation, not a physical claim. Von Neumann did not develop a theory of consciousness-induced collapse. He identified a gap in the formalism and noted that consciousness was one possible, not the only possible location for the cut. It was Eugen-Wigner who took the philosophical step. Wigner, born 1902, died 1995, Hungarian-American physicist, Nobel Prize in Physics 1963 for contributions to nuclear physics and symmetry principles, proposed in a 1961 essay that consciousness is the specific agent that causes wave function collapse. Wigner's reasoning was philosophical, not experimental. He argued that the measurement chain must terminate, that physical systems alone cannot explain why a single outcome is realized, and that consciousness, the one entity in the chain that is qualitatively different from physical matter, is the natural candidate for the collapse-inducing agent. In Wigner's famous thought experiment, Wigner's friend, a friend inside a laboratory performs a measurement and sees a definite result. Wigner, outside the laboratory, treats the entire laboratory, including his friend, as a quantum system in superposition, until he opens the door and asks. The question is, does the friend's consciousness collapse the wave function before Wigner looks? Wigner said yes. Consciousness, at any point in the chain, collapses the state. Let us examine this claim with the precision it demands. First, the evidence. There is no experimental evidence that consciousness causes wave function collapse. No experiment has ever demonstrated that the presence or absence of a conscious observer changes the outcome of a quantum measurement. Automated detectors, photomultiplier tubes, Geiger counters, CCD cameras produce definite outcomes without any human observer present. The outcomes are recorded on electronic media, stored in computer memory, and later read by humans. And the results are the same as if a human had been watching in real time. The interference pattern in the double-slit experiment vanishes when a witch path detector is placed at the slits, regardless of whether anyone is watching the detector. The key variable is the physical interaction between the detector and the particle, not the presence of a conscious mind. Second, the scope. If consciousness causes collapse, then every quantum system in the universe remained in superposition for 13.8 billion years, from the Big Bang through the formation of the first atoms, the first stars, the first galaxies, the first planets, the first molecules of prebiotic chemistry, until the first conscious being appeared. The first 13.8 billion years of cosmic history occurred in superposition. Stars formed in superposition. Galaxies assembled in superposition. Heavy elements were forged in supernovae in superposition. The Earth coalesced in superposition. All of this was indeterminate, a vast branching tree of unrealized possibilities, until a conscious brain appeared and collapsed the history into definiteness. This is not a minor claim. It is a claim that 99.9999% of cosmic history was ontologically indeterminate until a late arriving observer made it real. The claim is not supported by any evidence. It is contradicted by all geological, astrophysical, and cosmological evidence, which consistently shows that the universe behaved classically long before conscious life appeared. Third, the abandonment. Wigner himself abandoned the consciousness collapse interpretation. After learning of H. Dieter Zey's work on decoherence in the 1970s, the demonstration that environmental interactions produce effective collapse without any conscious observer, Wigner discarded his own proposal. He called it a form of solipsism, the philosophically untenable position that only one's own mind is real. The originator of the consciousness collapse interpretation looked at the physical evidence from decoherence and concluded that consciousness was unnecessary. He withdrew his own claim. This is not a disputed historical point. It is documented in the physics literature. Think about that. Take a moment. The physicist who proposed consciousness causes collapse, Eugene Wigner, Nobel laureate, one of the most distinguished physicists of the 20th century, examined the evidence from decoherence and concluded that his own proposal was wrong. He abandoned it. He called it solipsism. If the originator rejected it, the claim should have died in the 1970s. Instead, it was resurrected, not by physicists, but by popular authors, New Age speakers and filmmakers who either did not know or did not care that the idea had been abandoned by its own creator. The 2004 film, What the Bleep Do We Know?, and similar productions presented consciousness collapse as established physics. It is not. It is a discarded hypothesis, rejected by its originator, contradicted by decoherence, and unsupported by any experimental evidence. This brings us to decoherence, the physical process that actually explains the transition from quantum to classical, without consciousness, without mysticism, and without any special role for the observer. Decoherence is not a fringe theory. It is not a minority view. It is the mainstream explanation accepted by the physics community for why we never observe macroscopic superpositions, why cats are always alive or dead, why measurement apparatus always show definite readings, why the classical world appears solid, definite, and objective. Decoherence was first analyzed formally by H. Dieter Zeh, born 1927, died 2018, German physicist, in the 1970s. Zeh recognized that the measurement problem could be resolved, or at least dramatically reframed, by taking the environment seriously. Every quantum system interacts with its surroundings. No laboratory is perfectly isolated. No particle exists in a vacuum. Even the vacuum of interstellar space contains cosmic microwave background photons at 2.725 Kelvin, cosmic dust, neutrinos, and gravitational fluctuations. Zeh showed that these environmental interactions entangle the system with the environment, and this entanglement destroys the quantum coherence, the phase relationships between different components of the superposition that distinguishes a quantum state from a classical one. Wojciech Zurek, born 1955, Polish-American physicist at Los Alamos National Laboratory, developed the theory extensively from the 1980s onward, introducing key concepts: the pointer basis, Ein selection, environment-induced superselection, and quantum Darwinism. Zurek's contributions transformed decoherence from a qualitative insight into a precise quantitative framework with experimental predictions. The physics of decoherence can be stated precisely. A quantum system S in a superposition of states, say a combination of state A and state B, interacts with its environment E. The interaction entangles the system with the environment. The combined state of system plus environment becomes a superposition of system in A with environment recording A and system in B with environment recording B. The critical point is that the environment has an enormous number of degrees of freedom, trillions of photons, air molecules, thermal vibrations. When we trace out, mathematically discard, the environmental degrees of freedom, because we do not have access to every photon and molecule, the reduced state of the system alone becomes a statistical mixture. The off-diagonal terms in the density matrix, the terms that encode the coherent superposition, vanish. What remains is a classical probability distribution. The system is in state A, with probability given by the squared amplitude of A, or in state B, with probability given by the squared amplitude of B. The quantum superposition has become, for all practical purposes, a classical either-or. The timescales are staggering. A dust grain, 1 micrometer in diameter, roughly the size of a bacterium, in interstellar space, decoheres in approximately 10 to the negative 31 seconds upon absorbing a single photon from the cosmic microwave background. 10 to the negative 31 seconds, that is a billionth of a billionth of a billionth of a billionth of a millionth of a second. A nitrogen molecule in air at room temperature decoheres via molecular collisions in approximately 10 to the negative 36 seconds, 100,000 times faster than the dust grain. A macroscopic object at room temperature, a baseball, a cat, a measurement apparatus, decoheres so rapidly that the superposition lifetime is effectively 0. There is no window of time in which a macroscopic object exists in a quantum superposition under ordinary conditions. Decoherence is not slow. It is not gradual. It is, for macroscopic objects, effectively instantaneous. This is why we never see Schrödinger's cat in a superposition of alive and dead. The cat is entangled with the environment, with the air molecules in the box, with the thermal radiation, with the particles of the box itself, long before any conscious observer opens the lid. Decoherence has already enforced a classical outcome. By contrast, quantum coherence can be maintained in carefully engineered systems. A superconducting qubit, the basic unit of a quantum computer, can maintain coherence for approximately 10 to the negative 4 to 10 to the negative 6 seconds in a laboratory cooled to millikelvin temperatures and shielded from electromagnetic interference. This is long by quantum standards, long enough to perform thousands of quantum gate operations. But it is achieved only by extraordinary isolation from the environment. The moment the qubit interacts with uncontrolled environmental degrees of freedom, coherence is lost. Decoherence is the enemy of quantum computing, and the fact that enormous engineering effort is required to prevent it underscores how natural and ubiquitous the process is. In nature, without cryogenic shielding and electromagnetic isolation, decoherence is the default. Classical behavior is the default. Quantum coherence is the exception, maintained only in microscopic systems or under extreme laboratory conditions. The pointer states deserve particular attention because they answer a question that the consciousness interpretation cannot. Why does the classical world have the specific properties it has? Why do macroscopic objects have definite positions rather than definite momenta? Why are energy eigenstates relevant for atoms, but position eigenstates relevant for baseballs? The answer is einselection, environment-induced superselection. The specific form of the system-environment interaction determines which system states are resilient, which states survive environmental monitoring without being destroyed. If the environment couples to position, as photon scattering does for macroscopic objects, then position eigenstates are the pointer states. They survive decoherence and become the classical variables we observe. If the environment couples to energy, as in certain atomic systems, then energy eigenstates become the pointer states. The classical world is not arbitrary. It is selected by the environment, by the specific physical interactions that couple systems to their surroundings. Zurek calls this the quantum origin of the classical, and it requires no consciousness, no observer, and no mind. It requires physics. The density matrix, the mathematical representation of a quantum state that accounts for statistical mixtures and entanglement, evolves according to d rho over dt equals negative I over h bar times the commutator of h and rho. In a closed system, this is von Neumann's equation. The density matrix evolves unitarily, preserving superpositions. But when the system interacts with an environment, the dynamics include additional terms, the Lindblad operators, that describe the irreversible loss of coherence. The Lindblad master equation adds terms of the form sum over k of L sub k rho L sub k dagger minus 1/2 the anticommutator of L sub k dagger L sub k with rho. These terms cause the off-diagonal elements of the density matrix to decay exponentially. The superposition becomes, for all practical purposes, a classical mixture. The system is no longer in a combination of states. It is in one state or another, with probabilities given by the Born rule. No consciousness required. No observer required. The environment, photons, molecules, thermal radiation does the work. The total Hamiltonian of a system interacting with its environment is H equals H sub s plus H sub e plus H sub int. H sub s is the system Hamiltonian. H sub e is the environment Hamiltonian. H sub int is the interaction Hamiltonian, the term that couples the system to the environment. It is H sub int that causes decoherence. The specific form of H sub int determines which system states are resilient, which states survive environmental monitoring without being destroyed. These resilient states are the pointer states, the states that remain stable under the system-environment interaction. Position states, for example, are typically pointer states for macroscopic objects, because environmental scattering, photons, air molecules, monitors position. This is why macroscopic objects have definite positions and do not appear in superpositions of being here and there. Zurek's quantum Darwinism extends this picture. Not only does the environment cause decoherence, it also broadcasts information about the pointer states. When photons scatter off an object, they carry information about the object's position, size, and shape into the environment. Multiple observers, human or instrumental, can independently access different fragments of the environment and extract the same information about the object. The pointer states are the states whose information is redundantly encoded in the environment. This is why classical reality appears objective. Many independent observers agree on the state of the world, because the environment has broadcast the pointer state information to all of them. Zurek argues that classical states are accessed indirectly by observers via the imprints they leave in the environment, making our reality effectively objective. The observer does not create the result. The environment has already selected it, broadcasted, and made it available to anyone who looks. This is the part that stays with me. Not because it is dramatic, because it is precise. The environment monitors quantum systems continuously, at timescales of 10 to the negative 31 seconds for a dust grain, 10 to the negative 36 seconds for a molecule in air. The classical world is not created by consciousness. It is enforced by the environment, by the same photons, molecules, and thermal radiation that permeate every corner of the cosmos. The universe was classical, in the sense that decoherence was operative for 13.8 billion years before any conscious being existed to observe it. Stars formed, galaxies assembled, heavy elements were forged in supernovae, planets coalesced. All of this happened in the absence of any conscious observer. Decoherence was at work the entire time. Consciousness did not create this reality. Consciousness arrived late, approximately 13.8 billion years late, to a universe that was already overwhelmingly classical. Before we continue, consider what this means for the popular claim that you create your own reality. The claim is not merely wrong, it is the opposite of what the physics shows. The physics shows that the environment creates classical reality through decoherence, through ion selection, through the broadcast of pointer-state information into environmental fragments. The observer accesses a reality that has already been determined by physical processes. The observer does not participate in creating it. The double-slit experiment, the most frequently misquoted experiment in all of physics, deserves a careful, precise treatment because it is the experiment most commonly cited by consciousness advocates, and it is the experiment they most consistently misrepresent. In the standard double-slit experiment, particles, photons, electrons, or even large molecules are sent one at a time toward a barrier with two slits. If no detector monitors which slit the particle passes through, the particles accumulate in an interference pattern on the detection screen, a pattern of bright and dark bands that is the hallmark of wave-like behavior. The particle, in the quantum description, passes through both slits simultaneously. Its wave function traverses both paths, and the two components interfere constructively at some positions, bright bands, and destructively at others, dark bands. If a detector is placed at the slits to determine which slit the particle passes through, the interference pattern vanishes. The particles accumulate in two bands, one behind each slit, as if they were classical particles passing through one slit or the other. The consciousness interpretation claims that it is the conscious observation of which slit information that destroys the interference. The particle, according to this view, remains in superposition, passing through both slits until a conscious mind becomes aware of which slit it passed through. Consciousness collapses the wave function and destroys the interference. This is wrong. The interference vanishes because of the physical interaction between the detector and the particle, not because of conscious observation. When a which-path detector interacts with the particle, the detector becomes entangled with the particle. The detector acquires which-path information, and this entanglement destroys the coherence between the two paths. The interference vanishes because the phase relationship between the two path components is lost. the system has decohered through interaction with the detector. An automated detector with no human observer produces exactly the same result. A photon detector connected to a computer that records the data but is never read by a human destroys the interference pattern just as effectively as a detector watched by a physicist. The key variable is the physical entanglement between the particle and the detector, not the presence of a conscious mind. The experiment has been performed with increasingly large particles, demonstrating that quantum interference is a physical phenomenon governed by decoherence, not by consciousness. In 1999, Anton Zeilinger's group in Vienna demonstrated interference with fullerene molecules, C60, Buckminster fullerene, molecules containing 60 carbon atoms with a diameter of approximately 0.7 nanometers. The fullerenes exhibited clear interference patterns when passed through a diffraction grating in high vacuum. When the vacuum was degraded, allowing residual gas molecules to collide with the fullerenes, the interference pattern vanished. The decoherence was caused by molecular collisions, not by conscious observation. No one was watching the individual molecules. The environment, residual gas molecules, destroyed the coherence. This experiment is a direct empirical demonstration that decoherence, not consciousness, determines whether quantum interference is observed. The delayed choice experiment, proposed by John Wheeler, adds another layer that is frequently misinterpreted. In a delayed choice setup, the decision of whether to measure which path, or interference, is made after the particle has already passed through the slits. The result? The particle appears to retroactively change its behavior, displaying interference if the experimenter chooses the interference measurement, and no interference if the experimenter chooses the which path measurement, even though the particle has already traversed the slits. Wheeler described the observer as a participant in creating the past. This has been widely misquoted as evidence that consciousness determines reality retroactively. The correct interpretation is more subtle and does not involve consciousness. In the delayed choice experiment, the particle's state is not determined until the measurement is complete. But this is a feature of quantum mechanics, not of consciousness. The which path, or interference measurement, simply selects which quantum observable is being measured. The particle does not know in advance which measurement will be made. But the result does not depend on whether the experimenter is a human or an automated device. Wheeler himself later clarified that the participant concept does not imply mystical creation by mind. It means that the choice of experimental setup determines which quantum observable is realized. The setup is physical. The choice of apparatus is physical. Consciousness is not required. The quantum eraser experiment, a variant of the double slit, is equally misrepresented. In a quantum eraser, which path information is first recorded, destroying interference, and then erased by a subsequent measurement that destroys the which path record. When the eraser measurement is performed, the interference pattern reappears, but only in the subset of data correlated with the eraser outcome. The full pattern, without selecting the correlated subset, shows no interference. The quantum eraser does not demonstrate consciousness creating or uncreating interference. It demonstrates that quantum correlations, entanglement,
between the particle and the which path record can be manipulated by physical measurements, measurements that are equally effective whether performed by a human or a machine. No consciousness is involved. No mind is required. The physics is entanglement and measurement correlation, not observer-created reality. This brings us to Robert Lanza's biocentrism, the claim that consciousness is fundamental and that the universe is created by conscious observers. Lanza, born 1956, American biologist and medical researcher, published Biocentrism: How Life and Consciousness Are the Keys to Understanding the True Nature of the Universe in 2007. The book became popular in New Age circles and among readers who sought a scientific basis for the claim that consciousness creates reality. Let us apply the prosecution after defense model with full rigor. The defense. Lanza argues that quantum mechanics demonstrates the observer's centrality. The double-slit experiment shows that observation determines reality.
The delayed choice experiment shows that observation can influence the past. The measurement problem shows that without an observer, reality is indeterminate. Life and consciousness, in Lanza's view, are not accidental byproducts of a mindless universe, they are the primary reality. The physical universe exists because conscious beings observe it into existence. Space and time are not objective containers, but constructs of consciousness. Biocentrism, Lanza claims, is a new framework that resolves the measurement problem and explains fine-tuning by placing life at the center. The cross-examination. What does biocentrism actually explain? It claims consciousness creates reality, but it does not define consciousness in physical or operational terms. It does not specify the mechanism by which consciousness interacts with quantum systems. No equation, no Hamiltonian, no coupling constant. It does not make a single testable prediction that differs from standard quantum mechanics. If biocentrism were true, there should be observable differences between experiments performed by conscious observers and experiments performed by automated detectors. But there are none. Biocentrism does not explain decoherence, the experimentally confirmed physical process by which environmental interactions produce classical outcomes without consciousness. It does not explain how the universe existed for 13.8 billion years before conscious life appeared. 13.8 billion years of star formation, nucleosynthesis, and planetary geology, all of which left geological and astrophysical records consistent with classical physics operating without conscious observers. It does not explain why the Planck satellite, the Large Hadron Collider, and LIGO produce results consistent with objective physics, and not with observer-dependent reality. The prosecution. Biocentrism is not physics. It is a philosophical claim, specifically a form of idealism, dressed in the language of quantum mechanics. It misrepresents the double-slit experiment by conflating physical detection with conscious observation, ignoring the evidence from automated detectors and decoherence experiments with large molecules. It misrepresents the delayed choice experiment by attributing to consciousness what is actually a consequence of entanglement and measurement selection. It ignores the mainstream physical explanation, decoherence, that eliminates the need for consciousness in quantum measurement. It makes no falsifiable predictions. Any observation is, by definition, made by a conscious observer. So biocentrism would claim the observation was created by that observer, a circular argument that cannot be tested or refuted. By the standards of the scientific method, falsifiability, predictive power, mechanism, consistency with established physics, biocentrism fails on every count. It is pseudoscience, and it has been labelled as such by the mainstream physics community. The verdict? Biocentrism is not a scientific theory. It is a philosophical speculation that misrepresents quantum mechanics, ignores decoherence, and makes no testable predictions. The claim that consciousness creates reality is not supported by quantum mechanics. It is contradicted by decoherence theory, abandoned by the physicist who originally proposed consciousness collapse, rejected by the mainstream physics community, and refuted by every experiment that has tested the role of physical detectors versus conscious observers. The claim survives only because it tells people what they want to hear, that their consciousness is cosmically important, that they participate in creating reality, that mind shapes matter. The evidence says otherwise. The environment shapes the classical world. Consciousness is a witness, not a creator. This brings us to the interpretations of quantum mechanics, the competing frameworks for understanding what the mathematical formalism means, and to what they do and do not say about consciousness. There are several major interpretations, each with strengths and weaknesses, and none of them, with the single exception of the discarded consciousness interpretation, requires a conscious observer to explain measurement outcomes. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg in the 1920s and 1930s, is the oldest and most widely taught interpretation. Copenhagen holds that measurement by a macroscopic apparatus produces collapse. When a quantum system interacts with a classical measurement device, the wave function collapses to one of the device's pointer states, with probabilities given by the Born rule. The apparatus is treated as inherently classical. It has definite properties by assumption, and the quantum system is forced into definiteness by interaction with it. The classical quantum cut, the boundary between the quantum system and the classical apparatus, is the central feature and the central weakness of Copenhagen. Bohr, born 1885, died 1962, Danish physicist, Nobel Prize 1922, explicitly rejected the need for consciousness in measurement. According to Werner Heisenberg's recollection, Bohr stated that the observer plays no active role in collapse beyond selecting the experimental setup, choosing what to measure, not causing the outcome. The observer in Copenhagen is the measurement apparatus, not the observer's mind. The apparatus is classical, the system is quantum, and the interaction between them produces a definite result. No consciousness is invoked. The Copenhagen interpretation has been criticized for several reasons. The classical quantum cut is vague. It is never precisely defined where the quantum system ends and the classical apparatus begins. The collapse postulate is added ad hoc. It is not derived from the Schrödinger equation, but imposed as a separate rule. Critics, including John Bell, who called it unprofessionally vague, argue that Copenhagen hides the measurement problem rather than solving it. By declaring the apparatus to be classical, Copenhagen avoids the question of how classicality arises from quantum mechanics. Decoherence, in a sense, fills this gap. It explains why measurement apparatus are effectively classical, through environmental interactions that enforce pointer states. But Copenhagen predates decoherence and does not incorporate it into its formal structure. Whatever its weaknesses, Copenhagen does not invoke consciousness. Its observer is a piece of laboratory equipment. Its collapse is a physical interaction. The popular misunderstanding that the observer in quantum mechanics means a conscious human is a misreading of Copenhagen. A misreading that has been amplified by popular science books and films, and that Bohr himself would have rejected. The many worlds interpretation, proposed by Hugh Everett III in 1957, American physicist, born 1930, died 1982, takes a radically different approach. Everett took the Schrödinger equation at face value. It is universal, it never breaks down, and there is no collapse. When a measurement is performed, the Schrödinger equation predicts that the system plus apparatus plus observer enters a superposition of all possible outcomes. Everett proposed that all these outcomes are real, each in a separate branch of the universal wave function. When you measure a spin and see up, there is another branch where you see down. Both branches exist. Both are equally real. Your experience of a single outcome is simply your perspective from within one branch. Many worlds is mathematically elegant. It requires no collapse postulate, no Born rule as a separate axiom, though deriving the Born rule within many worlds remains controversial, and no special treatment of measurement. But it comes at an extraordinary cost. The existence of an unfathomable number of parallel branches, parallel versions of every measurement outcome, every quantum event, every interaction in the entire history of the universe. No evidence supports the existence of these other branches. No experiment has been proposed that could detect them. The interpretation is, by the admission of its proponents, unfalsifiable. No possible observation could confirm or deny the existence of the other worlds. Let us examine many worlds through the apologetic lens. The materialist finds many worlds attractive because it avoids collapse, and therefore avoids any need for an external agent, God, consciousness or otherwise, to choose an outcome. Every outcome happens. No choice is made. No agency is required. But the avoidance comes at the cost of multiplying unobservable entities to infinity. The multiverse of many worlds is not a single additional universe. It is an infinite, ever-branching tree of universes, one for every quantum event that has ever occurred anywhere in the cosmos, multiplied by every subsequent quantum event in every branch. This is not parsimony. It is extravagance beyond measure, invoked specifically to avoid the conclusion that measurement outcomes require an explanation beyond blind physics. And it does not explain why the Born rule holds, why we observe outcomes with frequencies proportional to the squared amplitude. The Born rule must be assumed or argued for by additional principles that are themselves debatable. Bohmian mechanics, The pilot wave theory, developed by David Bohm in 1952, American physicist, born 1917, died 1992, offers a deterministic alternative that is often overlooked in popular discussions. In Bohm's theory, particles have definite positions at all times. There is no superposition of macroscopic objects. There is no collapse. The wave function is real. It is a physical field that guides the motion of particles through a guiding equation, or pilot wave. The particle's trajectory is determined by the wave function's gradient, and the apparent randomness of quantum mechanics arises from ignorance of the initial particle positions, not from fundamental indeterminacy. If you knew the exact initial positions of all particles, you could predict every measurement outcome with certainty. Bohmian mechanics reproduces all the predictions of standard quantum mechanics. Every interference pattern, every Bell test violation, every quantum correlation. It does so without collapse, without observers, and without consciousness. In Bohm's theory, the double-slit experiment has a clear explanation. The particle goes through one slit, but the pilot wave goes through both, and the wave guides the particle to regions of constructive interference. No mystery, no consciousness, no observer creates reality. Just a particle with a definite position guided by a wave producing an interference pattern. The interpretation has weaknesses. The pilot wave is explicitly non-local. It responds to distant changes instantaneously, though no superluminal signal can be sent. And the hidden variables, particle positions, are not directly measurable. They are inferred from the theory. But for our purposes, the key point is that Bohmian mechanics demonstrates that quantum mechanics can be given a fully deterministic, consciousness-free interpretation that matches all experimental data. The claim that quantum mechanics requires consciousness is not merely unsupported, it is refuted by the existence of an alternative interpretation that works perfectly well without it. Objective collapse theories, such as the GRW model proposed by Giancarlo Girardi, Alberto Rimini, and Tullio Weber in 1986, and Roger Penrose's gravity-induced collapse proposal from 1989, modify the Schrödinger equation itself by adding a physical mechanism for collapse. In the GRW model, every particle has a small probability, approximately 10 to the negative 16 per second, of undergoing a spontaneous localization, a random, instantaneous collapse to a definite position. For a single particle, this rate is negligible. The particle evolves according to the Schrödinger equation for trillions of years before spontaneously collapsing. But for a macroscopic object containing 10 to the 23 or more particles, the rate scales linearly. At least one particle collapses every 10 to the negative 7 seconds, and the collapse of one particle drags the entangled wave function of the entire object into a definite state. The result? Microscopic systems behave quantum mechanically, rarely collapsing, while macroscopic systems behave classically, collapsing rapidly. The GRW model modifies quantum mechanics. It is not a reinterpretation, but a new theory, and it makes predictions that differ slightly from standard quantum mechanics. These predictions are being tested, though so far no experiment has detected spontaneous collapse. Penrose's proposal is different in mechanism, but similar in spirit. Penrose, born 1931, British mathematician and physicist, Nobel Prize 2020, suggested that quantum superpositions involving sufficiently different mass distributions and therefore different space-time geometries are gravitationally unstable and collapse spontaneously. The threshold is related to the Planck mass, approximately 22 micrograms. Below this threshold, superpositions are stable. Above it, gravity induces collapse. Like GRW, Penrose's proposal is a physical collapse mechanism, one that happens whether or not anyone is observing. It requires no consciousness, no mind, no observer. Gravity does the work. Penrose is also relevant to our fine-tuning discussion. He calculated that the probability of the Big Bang's initial conditions being arranged to produce the ordered, low-entropy universe we observe is approximately 1 part in 10 to the power of 10 to the 123. This is a number so large that it cannot be written in standard decimal notation. The exponent of the exponent is already 10 to the 123, a number with 123 digits. Penrose's calculation is one of the most striking quantitative statements about fine-tuning in the physics literature. The emerging cubism, or quantum Bayesianism, developed by Christopher Fuchs and others, and relational quantum mechanics, pioneered by Carlo Rovelli, offer different perspectives. Cubism treats the wave function as a tool for calculating probabilities based on the agent's beliefs, not as a description of objective reality. Relational quantum mechanics argues that quantum properties exist only in relation to observers, but observer here means any physical system capable of recording information, not specifically conscious entities. Neither interpretation requires consciousness to collapse wave functions or create reality. None of these interpretations, Copenhagen, many worlds, Bohmian mechanics, objective collapse, cubism, relational quantum mechanics, requires consciousness to explain measurement. In Copenhagen, a physical apparatus causes collapse. In many worlds, there is no collapse. All outcomes occur in branching universes. In Bohmian mechanics, outcomes are deterministic. Particles always have definite positions. In objective collapse models, physics triggers collapse. Stochastic events, GRW, or gravity, Penrose. In cubism, the wave function is epistemic, not ontological. In relational quantum mechanics, properties are relational but not consciousness-dependent. The consciousness interpretation, proposed in 1961, abandoned by its own originator in the 1970s, rejected by the mainstream physics community, and surviving only in popular culture, is the single outlier. It has no experimental evidence, it has no mechanism, it makes no testable predictions, and it was withdrawn by the physicist who proposed it. When I first understood this, that the claim consciousness creates reality was not just unsupported by physics, but explicitly contradicted by every mainstream interpretation and by the physical evidence from decoherence, the popular narratives I had absorbed fell apart. I had been told through documentaries and popular books that quantum mechanics proved the special role of consciousness, that the observer was central, that mind shaped matter. None of this was true. The physics said the opposite. The environment shapes the classical world through decoherence. The observer arrives after the fact, after the environment has already selected pointer states, destroyed coherence, and broadcast classical information. Consciousness is a witness to reality, not its creator. The distinction matters, not just scientifically, but philosophically. If consciousness creates reality, then reality is subjective, relative, and dependent on the observer. There is no objective truth. There is no external world independent of perception. This is philosophically convenient for those who wish to deny objective morality, objective truth, and objective design. Because if reality is observer-created, then there is nothing outside the observer to answer to. But if the environment creates classical reality, if reality is objective, pre-existing, and available to any observer who accesses the environmental record, then the universe has an independent existence. It has objective properties. It has measurable constants. And those constants are fine-tuned. The evidence supports objective reality. And objective reality demands an objective explanation for its fine-tuned precision. This brings us to the deeper question. The question that neither decoherence nor any interpretation of quantum mechanics can answer. Why do these laws exist? Why does the Schrödinger equation hold? Why does the Born rule give correct probabilities? Why is the fine structure constant approximately 1 over 137, a value that permits stable atoms, complex chemistry, and long-lived stars, and not some other number that would render the universe sterile? And why is the universe fine-tuned to a degree that secular physicists themselves describe in language that borders on awe? The consciousness mystics answered this question by putting consciousness at the center, by claiming that the universe exists because we observe it. We have examined that claim and found it empty. Decoherence refutes it. The evidence refutes it. The physicist who proposed it abandoned it. But the question remains. The universe does have extraordinarily precise constants. The laws do have a specific mathematical form, and neither decoherence nor any interpretation explains why. The fine structure constant, alpha, is given by alpha equals e squared over 4 pi epsilon sub 0 h bar c. This is a dimensionless number. It has no units. It is a pure ratio that determines the strength of the electromagnetic interaction between charged particles. E is the electron charge, approximately 1.602 times 10 to the negative 19 coulombs. Epsilon sub 0 is the vacuum permittivity, approximately 8.85 times 10 to the negative 12 farads per meter. H bar is the reduced Planck constant, approximately 1.055 times 10 to the negative 34 joule seconds. C is the speed of light, 299,792,458 meters per second, approximately 186,282 miles per second. The measured value of alpha is approximately 1 over 137.036, or equivalently, approximately 7.297 times 10 to the negative 3. This single number controls the structure of atoms. It determines how tightly electrons are bound to nuclei, how atoms interact with light, how chemical bonds form, and how fast chemical reactions proceed. If alpha were approximately 50% larger, if the electromagnetic force were 50% stronger, stellar nucleosynthesis would fail. Stars could not produce carbon and oxygen through the triple alpha process. No carbon means no organic chemistry. No organic chemistry means no biology. If alpha were changed by even a few percent in either direction, the periodic table of elements would be radically different, and the complex chemistry that underlies all known biology would not exist. The Stanford Encyclopedia of Philosophy's entry on fine-tuning notes that if the electromagnetic force were weakened by a similar amount, stellar nucleosynthesis would be inefficient, and stable stars of the type needed for life would not form. The fine structure constant is not derived from any known theory. It is measured. Its value is a brute fact, one that happens to permit atoms, molecules, chemistry, stars, and the conditions for complex structure. A different value, a value that falls outside a narrow range around 1 over 137, would produce a radically different, and in most cases, sterile universe. The cosmological constant, lambda, is the energy density of empty space, the vacuum energy that drives the accelerating expansion of the universe. In Planck units, the natural units of quantum gravity, the cosmological constant is approximately 10 to the negative 122. The natural value predicted by quantum field theory, the sum of zero-point energies of all field modes, is of order 1 in Planck units. The observed value is 122 orders of magnitude smaller. This is the cosmological constant problem, the largest discrepancy between theoretical prediction and experimental observation in the history of physics. If the cosmological constant were the natural value, if it were of order 1 in Planck units, or equivalently 10 to the 113 joules per cubic meter, space-time would curve so violently that no structures could form, no galaxies, no stars, no atoms, no molecules. The universe would be a featureless, exponentially expanding void, or a collapsed singularity, depending on the sign of lambda. If lambda were precisely 0, the universe would decelerate under the gravitational attraction of matter, and the specific large-scale structure we observe, the cosmic web of filaments and voids, the distribution of galaxies, the expansion history, would be different. The observed value is neither the natural enormous number nor 0. It is a specific, extraordinarily small, non-zero number that permits the formation of galaxies, stars, and complex structure. Leonard Susskind, born 1940, American string theorist at Stanford, stated, "To make the first 119 decimal places of the vacuum energy 0 is almost certainly no accident." Susskind is not a theist. He favors the multiverse as an explanation, but his words acknowledge what the data shows. The precision is extraordinary, and accident is an inadequate explanation. Fred Hoyle, born 1915, died 2001, British astrophysicist, made one of the most striking predictions in the history of nuclear physics. In 1954, Hoyle predicted that the carbon-12 nucleus must have a specific excited energy state at approximately 7.65 mega-electron volts, a resonance level that enables the triple alpha process to produce carbon efficiently inside stars. Without this resonance, carbon production would be negligibly slow, and the universe would contain almost no carbon, and therefore no organic chemistry and no carbon-based life. The resonance was subsequently discovered experimentally at almost exactly the energy Hoyle predicted. The precision is at the level of a few electron volts out of 7.65 million electron volts, tuning at the 1 in 10 to the 5 level. Hoyle, reflecting on this discovery, stated, "A super-intellect has monkeyed with physics, as well as with chemistry and biology, and the numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question." Hoyle was not a conventional theist. He used the word super-intellect rather than God. But his conclusion is clear. The precision points to deliberate configuration. Paul Davies, born 1946, British cosmologist and theoretical physicist, wrote, "It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming." Davies is an agnostic, not a theist. Yet the evidence compelled him to describe what he observed as design, a word with inescapable implications. Martin Rees, born 1942, British Astronomer Royal, cosmologist, wrote in just 6 numbers that 6 fundamental constants constitute a recipe for a universe, and that, if any one of them were untuned, there would be no stars and no life. Rees identifies the 6 numbers: the ratio of electromagnetic to gravitational force, approximately 10 to the 36, the strength of the strong nuclear force, approximately 0.007, the cosmic density parameter omega, approximately 1 within tight bounds, the cosmological constant lambda, the primordial density fluctuation amplitude q, approximately 10 to the negative 5, and the number of spatial dimensions, 3. Each of these numbers falls within a narrow range that permits complex structure. Change any of them by modest amounts, and the universe is sterile. Lee Smolin, born 1955, American theoretical physicist, calculated that the probability of randomly chosen physical constants producing a life-supporting universe is approximately 1 in 10 to the 229. 10 to the 229. A number with 229 digits. For comparison, the number of atoms in the observable universe is approximately 10 to the 80. The probability of a life-supporting universe by chance is smaller than 1 divided by the number of atoms in the universe raised to approximately the 3rd power. This is not unlikely. This is, for all practical and philosophical purposes, impossible by chance. Roger Penrose, as we noted, estimated the precision of the Big Bang's initial conditions at 1 part in 10 to the power of 10 to the 123. This number is so large that writing it in standard notation would require 10 to the 123 digits. More digits than there are particles in the observable universe by a factor of 10 to the 43. Penrose is not a theist. He does not draw the theistic conclusion. But the number he calculated is a datum, and the datum demands an explanation. Think about those quotations and those numbers. These are not theists. These are secular physicists. Susskind, Hoyle, Davies, Rees, Smolin, Penrose, describing the evidence they observe. The language they use, no accident, super-intellect, design, overwhelming, recipe, untuned, is the language of intention, precision, and purpose. They use this language because the evidence compels it. The fine-tuning is not a philosophical argument imposed on the data. It is a feature of the data that the physicists themselves acknowledge. What would you conclude from this evidence if you followed it honestly? The materialist response to fine-tuning is the multiverse, the proposal that our universe is one of an infinite ensemble of universes, each with different physical constants, and that we observe life-friendly constants simply because we exist in a life-friendly universe. No designer needed, just probability across infinite trials. Let us apply the prosecution after defense model. The defense. The multiverse is proposed in some versions of cosmic inflation, eternal inflation, the string landscape. It is discussed by serious physicists. It provides a framework in which fine-tuning is not mysterious. It is inevitable, given enough trials. The cross-examination. The multiverse has zero observational evidence. No other universe has been observed, measured, or detected. No instrument has been built or proposed that could observe another universe. The theory is not falsifiable. No possible observation could prove it wrong. If there were only one universe, the data would look identical. The multiverse adds nothing to the observations. It is invoked not because the evidence demands it, but because the alternative, design, is philosophically unacceptable to those who have committed a priori to naturalism. The prosecution. By the standards of the scientific method, observation, experimentation, falsifiability, reproducibility, the multiverse is not science. It is philosophical speculation dressed in the language of physics. It violates the principle of parsimony. Instead of one universe requiring explanation, it posits an infinite number of universes, none of which is observable. And even if infinite universes existed, the mechanism generating them, eternal inflation, the string landscape, or whatever process produces the ensemble, would itself require laws, initial conditions, and fine-tuning. Where did the laws of inflation come from? Why does the string landscape have the specific structure it does? The multiverse does not eliminate the need for an explanation. It pushes the question back one level, and at that level, the same fine-tuning problem recurs. The regress is not resolved, it is multiplied. The verdict: the multiverse is not an explanation. It is an escape route, an attempt to avoid the conclusion that fine-tuning implies a fine-tuner. But the escape fails. The evidence still points in one direction. The materialist might respond, "We don't know yet. Science will eventually explain it." Let us examine this response. "We don't know yet, but science will figure it out," is not an argument. It is a statement of faith. Faith in the capacity of future scientific discoveries to resolve a question that may lie beyond the scope of science. Science describes how the universe operates within a framework of laws. It cannot explain why those laws exist. The Schrödinger equation describes quantum dynamics. It does not explain why quantum mechanics holds. The Born rule gives correct probabilities. It does not explain why probabilities take this specific form. The fine structure constant is measured at 1/137. It is not derived from any known theory. The cosmological constant is measured at 10 to the negative 122 in Planck units. No theory explains this value. Science will explain it is faith in a future that may never arrive, deployed to avoid a conclusion the materialist finds uncomfortable. The structural limitation is real. Science operates within a framework. It assumes the existence of natural laws, proposes hypotheses about those laws, tests the hypotheses through experiment, and refines them. This method is extraordinarily powerful for describing the behavior of systems that already exist. It cannot explain why the framework exists. No equation within physics can explain why equations hold. No law within physics can explain why laws exist. The question, why do these laws exist, is not a physics question. It is a metaphysical question, and it demands a metaphysical answer. The consciousness argument is directly relevant here, but not in the way the mystics claim. The hard problem of consciousness, identified by philosopher David Chalmers, remains unsolved by materialist philosophy and neuroscience. Atoms have no awareness. Molecules have no thoughts. Neurons fire electrical signals. Approximately 100 billion neurons in the human brain, forming approximately 100 trillion synaptic connections. But the transition from electrical signals to subjective experience has no materialist explanation. Neuroscience can correlate brain states with mental states. This brain region is active during visual processing, that region during emotional response. This pattern accompanies the experience of pain. But correlation is not explanation. The question is not where consciousness correlates in the brain. The question is how physical processes, which are at bottom arrangements of quarks, electrons and photons obeying the Schrödinger equation and the Standard Model, give rise to subjective first-person experience. How does the firing of neurons produce the experience of seeing red? How does electrochemical activity become the feeling of grief? How does quantum electrodynamics become the sensation of warmth? No materialist theory has answered this question. Functionalism says consciousness is what the brain does. But this is a description, not an explanation. Computationalism says consciousness is information processing. But a thermostat processes information without being conscious. Emergentism says consciousness emerges from complexity. But emergence is a word, not a mechanism. The claim that complex arrangements of unconscious particles produce consciousness is not an explanation. It is a restatement of the problem in different words. The hard problem remains hard. The consciousness mystics exploit this gap by claiming that consciousness is fundamental, that it exists prior to matter and creates reality through quantum observation. We have examined this claim and found it contradicted by decoherence, abandoned by its originator, and unsupported by evidence. But the gap is real. Consciousness exists. It is not explained by materialism. And the existence of consciousness in a universe of unconscious particles is itself a datum that demands explanation. Now let us follow the evidence where it leads. Something has always existed. The chain of causes must terminate. If every cause requires a prior cause stretching back infinitely, nothing would ever begin, and we would not exist. The fact that we exist proves the chain terminates. Something eternal, uncaused, self-sufficient, and independent must exist. The evidence demands specific attributes of this eternal something. Power, sufficient to bring a universe into existence with 10 to the 70 joules of mass energy. Knowledge, sufficient to configure physical constants to 1 part in 10 to the 120, the cosmological constant, to 1 part in 10 to the 5, the carbon resonance, to the specific value of 1/137, the fine structure constant, against odds that Lee Smolin calculates at 1 in 10 to the 229, and Roger Penrose estimates at 1 in 10 to the power of 10 to the 123. Will, because a specific configuration was selected from an infinite landscape of alternatives. Selection is an act. Acts require agents. Agents that select possess will. The constants could have been different. They are what they are because a choice was made. These are the attributes of a creator: power, knowledge, will, eternality, independence from the physical universe because the universe's laws are among the things that require explanation. Whatever configured the Schrödinger equation, the Born rule, the fine structure constant, the cosmological constant, the carbon resonance, the neutron-proton mass difference, and the primordial density fluctuation amplitude did so from outside the framework defined by those laws. The configurator is not subject to the configuration. The lawgiver is not bound by the laws. I return to this point often, not because it is comfortable, because it is true. The most fundamental questions: why do these laws exist? Why is consciousness possible? Why are the constants fine-tuned to degrees that secular physicists call overwhelming and beyond question? Are precisely the questions that physics cannot answer. Not because physics is wrong, not because physics is incomplete, because the questions are about the existence of the framework within which physics operates, and no framework can explain its own existence. The explanation must come from outside the framework. The evidence points to an intelligence that precedes the framework, configured the framework, and brought it into existence with deliberate precision. Let us now assemble the full evidence file. Every datum, every equation, every experiment, every argument, and state the conclusion plainly. Quantum mechanics is real. The Schrödinger equation I h bar d psi over dt equals h psi describes quantum dynamics with precision confirmed by every experiment in the history of physics. The Born rule, probability equals squared amplitude, gives correct measurement outcomes confirmed by billions of experimental trials across a century of quantum physics. The Heisenberg uncertainty principle, delta x delta p greater than or equal to h bar over 2, establishes fundamental limits on simultaneous measurement precision, confirmed by every precision experiment in atomic and subatomic physics. Superposition is real. It has been confirmed with photons, electrons, neutrons, atoms, and molecules as large as fullerenes, Zeilinger, 1999, and even larger organic molecules in subsequent experiments. Entanglement is real. It has been confirmed by Bell test violations. The Bell test experiments deserve explicit treatment as concrete grounding for the reality of quantum mechanics. In 1964, John Bell, born 1928, died 1990, Northern Irish physicist at CERN, formulated Bell's theorem. No theory of physics based on local hidden variables can reproduce all the predictions of quantum mechanics. Specifically, Bell derived an inequality, a mathematical bound on the correlations between measurements on two separated particles, that any local hidden variable theory must satisfy. Quantum mechanics predicts violations of this inequality for entangled particles. If Bell's inequality is violated in experiments, local hidden variable theories are ruled out, and quantum mechanics, with its non-local correlations, is confirmed. The implications of Bell's theorem cannot be overstated. Before Bell, it was possible to believe that quantum mechanics was incomplete, that behind the probabilities lay a deeper, deterministic reality in which particles had definite properties at all times, and the apparent randomness was merely ignorance of these properties. This was Einstein's position. Einstein, Podolsky, and Rosen had argued in their famous 1935 paper that quantum mechanics must be incomplete because it predicted spooky correlations between distant particles that seemed to violate locality, the principle that distant events cannot instantaneously influence each other. Bell showed that this was not a matter of interpretation or philosophy. It was a matter of experiment. If the correlations between entangled particles exceeded the Bell inequality bound, then no local hidden variable theory, no theory in which particles carry predetermined properties and in which no influence travels faster than light, could account for the data. Quantum mechanics would be the only viable framework. In 1982, Alain Aspect, born 1947, French physicist at the Institut d'Optique in Orsay, near Paris, conducted the experiments that settled the question. Aspect's team used pairs of entangled photons produced by calcium atoms excited by lasers. The photons were sent to two detectors separated by approximately 12 meters, roughly 39 feet. The key innovation was the use of rapidly switching polarizers, acousto-optic switches that changed the measurement setting every 10 nanoseconds, faster than light could travel between the two detectors. At 12 meters separation, light takes approximately 40 nanoseconds. This ensured that the measurement setting at one detector could not influence the outcome at the other through any signal traveling at or below the speed of light, closing the locality loophole. The result was decisive. Bell's inequality was violated by approximately 5 standard deviations. The correlations between the photons were exactly as quantum mechanics predicted and exceeded the maximum allowed by any local hidden variable theory. The experiment was repeated with increasing precision in subsequent decades, by Weiss in Vienna in 1998, increasing the separation to hundreds of meters, by Justina and others in 2015, closing both the locality and detection loopholes simultaneously, and by many other groups. Modern Bell tests achieve violations exceeding 10 standard deviations with detection efficiencies above 98%. The locality loophole, the detection loophole, and the freedom of choice loophole have all been addressed. Aspect, John Causer, and Anton Zeilinger shared the 2022 Nobel Prize in Physics for these contributions. What Bell tests demonstrate, for our purposes, is that quantum mechanics is not a provisional theory or a convenient approximation. It is the most precisely confirmed theory in the history of physics. The correlations it predicts are real. The superpositions it describes are real. The wave function is not merely a mathematical tool. It captures something genuine about the physical world. And the classical world we observe, the world of definite positions, definite pointer readings, and definite experimental outcomes, arises from quantum mechanics through a specific physical process, decoherence. Not through consciousness, not through mystical observation, through the interaction of quantum systems with their environments. The concrete grounding extends beyond Bell tests. Consider the following examples from the research that anchor abstract quantum physics in real events. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves from merging black holes in 2015. LIGO operates at the quantum limit. Its detection sensitivity, approximately 10 to the negative 21 meters, a thousandth of a proton diameter, is limited by quantum shot noise, the random fluctuations in photon number inherent to laser light. LIGO's detectors are, in a real sense, quantum instruments measuring classical cosmic events. The gravitational wave signal, a chirp lasting approximately 0.2 seconds, was a classical outcome produced by the decoherence of a quantum detection system. No consciousness was required. The LIGO detectors were automated. The signal was recorded digitally. Human physicists analyzed the data weeks later. The detection occurred without any human observer present. The Challenger disaster of 1986, the Space Shuttle Challenger broke apart 73 seconds after launch due to an O-ring failure in the solid rocket booster, caused by cold temperatures that made the rubber brittle, serves as an analogy for fine-tuning. A small change in temperature, a few degrees Celsius, led to catastrophic failure. The tolerance was narrow. The system depended on precise conditions. The analogy to cosmic fine-tuning is direct. Small changes in physical constants lead to catastrophic failure of the universe's ability to produce stars, atoms, and chemistry. The Soyuz 11 depressurization in 1971, 3 cosmonauts died when a cabin pressure valve failed during re-entry, underscores the same point. The margin between function and failure is narrow. Life depends on precise engineering, whether in a spacecraft or in the constants of physics. Hoyle's carbon resonance prediction is perhaps the most striking example of fine-tuning grounded in real experimental physics. In 1954, Fred Hoyle calculated that for stars to produce carbon through the triple alpha process, in which 3 helium-4 nuclei, alpha particles, combine to form carbon-12, there must exist a specific excited state of the carbon-12 nucleus at approximately 7.65 mega-electron volts above the ground state. Without this resonance, the triple alpha reaction would be far too slow to produce appreciable carbon. Hoyle predicted the resonance level before it was experimentally confirmed. When nuclear physicists measured the carbon-12 energy levels, they found the resonance at 7.6549 mega-electron volts, within a few electron volts of Hoyle's prediction. The precision of this match, and the fact that the existence of carbon, and therefore organic chemistry, and therefore biology, depends on this specific nuclear energy level, is one of the most concrete examples of fine-tuning in physics. It is not an abstract philosophical argument. It is a measured nuclear energy level that, if different by a small amount, would render the universe devoid of carbon. The cosmological instruments provide the broader context. The Planck satellite, ESA 2009-2013, final data released 2018, measured the cosmic microwave background radiation with the highest precision ever achieved. The CMB is the thermal relic of the early universe. The radiation released approximately 380,000 years after the Big Bang, when the universe cooled sufficiently for atoms to form and photons to travel freely. The Planck satellite mapped this radiation across the entire sky at 9 frequency bands, producing maps of temperature and polarization with angular resolution down to approximately 5 arc minutes. Planck confirmed the flat geometry of space. Omega sub tot equals 1.0007 plus or minus 0.0019, flat to within 0.2%. Planck determined the age of the universe at 13.80 plus or minus 0.02 billion years. The Hubble constant at approximately 67.4 kilometers per second per megaparsec, approximately 41.9 miles per second per megaparsec, and the cosmic composition, approximately 4.9% normal baryonic matter, approximately 26.8% dark matter, and approximately 68.3% dark energy, vacuum energy. These numbers are the measured properties of the universe. They are precise, they are not negotiable, and they describe a universe with specific, quantifiable, fine-tuned properties. WMAP, the Wilkinson Microwave Anisotropy Probe, was a NASA satellite that operated from 2001 to 2010. WMAP provided the first high-precision measurements of the CMB angular power spectrum, determining the age of the universe at approximately 13.77 billion years, and establishing the concordance cosmological model, the lambda CDM model, with its specific proportions of matter, dark and dark energy. WMAP's data confirmed inflationary predictions. The spatial flatness of the universe and the nearly scale-invariant spectrum of primordial density fluctuations. COBE, the Cosmic Background Explorer, was a NASA satellite that operated from 1989 to 1993. COBE discovered the tiny CMB temperature anisotropies, fluctuations of approximately 1 part in 100,000 that represent the seeds of cosmic structure. These fluctuations, stretched from quantum-scale vacuum fluctuations during inflation to cosmological scales by the exponential expansion, seeded the formation of galaxies and galaxy clusters. COBE's discovery earned John Mather and George Smoot the Nobel Prize in Physics in 2006. The Large Hadron Collider, a 27-kilometer circumference proton-proton collider at CERN, accelerates protons to energies of 6.5 TeV per beam, producing collisions at a center of mass energy of 13 TeV. In 2012, the ATLAS and CMS experiments discovered the Higgs boson at a mass of approximately 125 giga-electron volts. The Higgs field permeates all of space with a non-zero vacuum expectation value of approximately 246 giga-electron volts, confirming that empty space is not empty. It is filled with a quantum field at a specific measured non-zero value. The Higgs field gives particles their masses through electroweak symmetry breaking. Without the Higgs field, without its specific vacuum expectation value, the W and Z bosons would be massless. The weak force would be long range, and the chemistry that produces atoms, molecules, and life would not exist. The Higgs field is another fine-tuned feature of the universe. Its vacuum expectation value must be approximately 246 giga-electron volts for the standard model to produce the particle spectrum we observe. LIGO and Virgo detected gravitational waves from merging black holes in September 2015, the first direct detection of gravitational waves, validating a prediction of Einstein's general relativity made exactly 1 century earlier. The detection sensitivity of LIGO, approximately 10 to the negative 21 meters, or 1,000th of the diameter of a proton, is limited by quantum shot noise in the laser light. LIGO is a quantum instrument measuring classical cosmic events. The 2017 detection of gravitational waves from a binary neutron-star merger, accompanied by electromagnetic radiation across the spectrum from gamma rays to radio waves, confirmed that neutron-star mergers are sites of heavy element nucleosynthesis, producing elements like gold, platinum, and uranium through the rapid neutron capture process, R process. These observations confirm the framework of physics, general relativity, quantum mechanics, nuclear physics, within which every argument about consciousness, decoherence, and fine-tuning operates. The framework is measured, it is confirmed, and the framework's specific fine-tuned properties demand an explanation that physics itself cannot provide. The James Webb Space Telescope, JWST, launched December 2021, observes the universe in infrared, studying galaxies at redshifts greater than 10, galaxies forming 300 to 500 million years after the Big Bang, JWST extends our observational reach to the earliest epochs of structure formation, providing data on the first stars, the first galaxies, and the chemical enrichment of the early universe. These observations constrain models of cosmic development, but do not probe the origin of the laws themselves. No instrument can observe why the Schrödinger equation holds, or why the fine structure constant is 1 over 137. These instruments confirm the data. They confirm the precision. They confirm the fine-tuning. And they confirm that the questions why these laws, why these constants, why this universe, lie beyond the reach of any telescope, any collider, and any gravitational wave detector. The data is the data. The question is what the data means, and whether the physicist has the courage to follow the evidence where it leads. The claim that consciousness creating reality is a myth. This conclusion rests on multiple independent lines of evidence, not on a single argument. First, the von Neumann-Wigner interpretation, the original claim that consciousness causes wave function collapse, was proposed by Eugene Wigner in 1961. Wigner himself abandoned it in the 1970s after Zay's decoherence work, calling it a form of solipsism. The originator of the claim examined the evidence and withdrew it. The idea is now classified by physicists as a historical interpretation, largely abandoned by the physics community since the 1970s and 1980s. Second, decoherence, developed by H. Dieter Zay, 1970s, and Wojciech Zurek, 1980s onward, provides a complete physical explanation for the transition from quantum to classical without any role for consciousness. Environmental interactions entangle quantum systems with their surroundings, destroying coherence and selecting pointer states. The timescales are measured: 10 to the negative 31 seconds for a micrometer dust grain, 10 to the negative 36 seconds for a nitrogen molecule in air. The classical world is enforced by the environment, continuously, ubiquitously, at timescales far too short for consciousness to play any role. Third, quantum Darwinism, Zurek's framework, explains how the environment broadcasts redundant copies of pointer state information, making classical reality objective and accessible to multiple independent observers. The observer does not create the outcome. The environment has already selected it, recorded it, and broadcast it. Classical reality is a product of physics, not of perception. Fourth, the double-slit experiment, the experiment most commonly misquoted by consciousness advocates, demonstrates that physical detection, any interaction that reveals which path information, destroys interference, regardless of whether a conscious observer is present. Automated detectors produce the same results as human-observed detectors. The Fullerene experiments, Zeilinger, 1999, confirmed that environmental interactions, residual gas molecules, not consciousness, cause decoherence. The delayed choice experiment shows that measurement selection determines the quantum observable, not that consciousness retroactively creates the past. The quantum eraser demonstrates entanglement correlations manipulable by physical measurements, not by consciousness. Fifth, Robert Lanza's biocentrism, the The claim that consciousness is fundamental and creates reality fails every test of scientific validity. Falsifiability, predictive power, mechanism, and consistency with established physics. It misrepresents quantum experiments, ignores decoherence, and offers no testable predictions that differ from standard quantum mechanics. Sixth, no interpretation of quantum mechanics, Copenhagen, many worlds, Bohmian mechanics, objective collapse, cubism, relational quantum mechanics requires consciousness. In Copenhagen, a physical apparatus causes collapse. In many worlds, there is no collapse. In Bohmian mechanics, outcomes are deterministic. In objective collapse models, GRW, Penrose, physics triggers collapse. In cubism, the wave function is epistemic. In relational quantum mechanics, properties are relational, but not consciousness-dependent. The consciousness interpretation is the single outlier, proposed in 1961, abandoned by its originator, rejected by mainstream physics. The fine-tuning of physical constants is real. It is acknowledged by secular physicists. The fine structure constant, at approximately 1/137, permits stable atoms and complex chemistry. A few percent change would be catastrophic. The cosmological constant is tuned to 1 part in 10 to the 122 in Planck units, the largest discrepancy in physics between theory and observation, at a value that permits galaxy formation. Carbon resonance at 7.65 mega-electron-volts, predicted by Hoyle in 1954, confirmed experimentally, enables carbon production in stars with 1 in 10 to the 5 precision. The neutron-proton mass difference of 1.29 mega-electron-volts is within the narrow range permitting stable nuclear physics. Lee-Smolin calculated the probability of life-supporting constants at 1 in 10 to the 229. Roger Penrose estimated the precision of Big Bang initial conditions at 1 in 10 to the power of 10 to the 123. Fred Hoyle. A super-intellect has monkeyed with physics. The numbers seem to me so overwhelming as to put this conclusion almost beyond question. Paul Davies. The impression of design is overwhelming. Martin Rees. If any one of 6 fundamental numbers were untuned, there would be no stars and no life. Leonard Susskind. To make the first 119 decimal places of the vacuum energy 0 is almost certainly no accident. These are secular physicists. They are not theists. They are describing the evidence. The multiverse, proposed to explain fine-tuning without a designer, has 0 observational evidence, is unfalsifiable, and does not solve the problem, but pushes it to the mechanism generating universes, which itself requires laws and fine-tuning. Science will eventually explain it is not an argument, but faith in future discoveries. Faith deployed to avoid a present conclusion. The hard problem of consciousness remains unsolved by materialism. Atoms have no awareness. Molecules have no thoughts. No arrangement of unconscious particles has ever been shown to produce subjective experience. The materialist claim that mind arose from mindless matter is a philosophical commitment, not a conclusion from evidence. The chain of causes must terminate. An infinite regress of dependent causes would never reach the present. Something eternal, uncaused, self-sufficient, and independent must exist. The evidence demands specific attributes. Power, a universe with 10 to the 70 joules of mass energy. Knowledge, constants tuned to 1 part in 10 to the 120. Will, a specific configuration selected from an infinite landscape. Eternality, preceding time and space. And independence, not bound by the laws it configured. These are the attributes of a creator. Quantum mechanics, the Schrödinger equation, the Born rule, decoherence, pointer states, quantum Darwinism, einselection, the measurement problem, the density matrix, the Lindblad master equation, the Heisenberg uncertainty principle, the fine structure constant at 1/137, the cosmological constant tuned to 1 part in 10 to the 122, carbon resonance at 7.65 mega-electron-volts, the neutron-proton mass difference at 1.29 mega-electron-volts, aspects Bell test, Zeilinger's fullerene interference, Zurek, Zay, Wigner, who proposed consciousness collapse and abandoned it, von Neumann, who identified the measurement chain ambiguity but did not invoke consciousness, Lanza, whose biocentrism fails every scientific test, Bohr, who rejected the need for consciousness by 1927, Hoyle, Davies, Rees, Susskind, Smolin, Penrose, Planck satellite, WMAPCOBE, the LHC, LIGO. 13.8 billion years of cosmic history. Decoherence at 10 to the negative 31 seconds. Fine-tuning at 1 in 10 to the 229 against. Initial conditions at 1 in 10 to the power of 10 to the 123. The consciousness mystics claim you create reality with your mind. The evidence says the environment creates classical reality through decoherence, a physical process that operates at timescales of 10 to the negative 31 seconds in every corner of the cosmos for 13.8 billion years before any conscious being existed to observe it. The materialist claims unconscious matter produced conscious observers through blind, unguided processes, and the fine-tuning is an accident or explained by an unobservable multiverse. The evidence says the fine-tuning spans 120 to 229 orders of magnitude of precision, acknowledged by secular physicists as overwhelming, and no materialist explanation survives scrutiny. The evidence does not point to consciousness creating reality. It does not point to the multiverse. It does not point to blind, unconscious matter producing order, information, consciousness, and mathematical precision by accident across infinite time. The evidence points to an intelligent, powerful, eternal creator, one who set the Schrödinger equation, configured the Born rule, established the fine structure constant at 1/137, tuned the cosmological constant to 10⁻⁻122, arranged the carbon resonance at 7.65 mega-electron volts, and brought into existence a universe whose precision, order, mathematical elegance, and capacity for conscious observation testify to the attributes of its maker. Power, knowledge, will, eternality, independence. That is not faith against evidence. That is the conclusion the evidence demands when examined honestly. That conclusion, once reached, changes everything. Good night.